Welcome, everybody. My name is Mary Ann Francis, and I am a member of the Search Mastery Interest Group, and I'd like to welcome you to the second of our fall Search Mastery Speaker Series, where we explore the foundations and practice of search, skills, education, and literacy. And today, we're really happy and excited to have Doug Oard with us. And he'll be telling us about searching the world and finding and using content in other languages. And just as a brief introduction to Doug, he's a professor here at the University of Maryland, and he has joint appointments in the College of Information Studies, as well as the University of Maryland Institute for Advanced Computer Studies. He has a passion for building search engines for text, speech, and scanned documents that might be in any language. Thank you, Doug, for joining us. We're looking forward to hearing this really super interesting talk.
My pleasure. Thanks for the introduction. Let me start sharing screen. Do
Okay,
you want to go yours?
You should be able to take right over.
Okay, I will try to steal it. Let's see. How's about that? Are you seeing it?
Yes, I am.
Very good. Thanks again for inviting me. What I wanted to talk about today is weird search engines. My research is in building search engines, not in using them, but building them. And I depend critically on people who think seriously about using them so that the things that we're building are in fact useful. And what I'll try to talk about today is what kinds of things we're trying to build, how we're trying to build them, and what thinking we have already in how to think about what might be useful, what additional capabilities these search engines might need. And so let me just start out with a quick sort of taste of the kinds of search engines that we're building that you can actually try at home. So this is a search engine called Twolingual. And you can see here, it looks a little like Google. You just type in your query. So this query is Ebola, New York City. You type in the query in English and you search English on the left. And in fact, those are Google search results in English. Twolingual is owned by Google. And on the right, what you see are what would have happened if you had translated the query into Spanish before typing it, and you get back Spanish documents, not at all surprisingly. You can try this out with a variety of languages and see what kinds of things you get. Now, Google has the ability to translate. So if you do this in Chrome, you'll get a little translate button in the upper right. And after you've clicked on a document, you can translate that document back into English and get a sense for what it's about. Now, you won't be able to read it in the same way that you could have read it if it was a native English language document. Translation is sometimes so wrong it's funny. But usually you can get a sense for what it's about, and often you can pull content out of it. So before we started today, I was playing around with a search, which I'd recommend, in traditional Chinese characters, so Chinese characters used in Taiwan, University of Maryland, and you'll see that you get back some things that you can then have translated that give you a sense for what they're talking about in Taiwan about the University of Maryland. Now, let me, rather than spend time on a demo there, go on and talk about why we're doing this in the first place. So this is a picture of the languages of the world. Here you can see that English is more widely spoken than Chinese. Now that might surprise you because there are more, of course, native Chinese speakers than there are native English speakers, and that's what the blue bar is. So this L1 are people who are first language speakers of Chinese. And there are more first language speakers of Chinese than of any other language in the world because the blue bar is longer than any of the other blue bars. The orange bar are the people who speak Chinese as a second language or who speak English as a second language or, all the way down. And you can see, for example, there are very few second language speakers of Turkish. And now if you look at the picture, you see that there are about as many speakers of English as there are speakers of Chinese, and that together English and Chinese are both about a sixth or so, somewhere between 15 and 20% of the speakers in the world, right? If there are about 7 billion people in the world, you can do that math pretty easily. The problem is in this table here. So this is not every web page on the web, but it's the most popular web pages. And it's the most popular 10 million web pages. So it's got a pretty good coverage of the actual web pages getting used. And what you can see here is that 63% of the web, this is as of last week, the language data was from 2018, but 63% of the web pages are in English. And so what that says is that the people who are searching in English, who issue their queries in English and thus find web pages in English, are privileged. They're getting essentially better service. And if you scan down to see Chinese, you'll see that 1.4% of the web pages are in Chinese. Well, that's a tremendous disparity, right? I mean, you've got just as many Chinese speakers, give or take, as you have English speakers doing searches, and there's so much less information to find in Chinese. It's actually even worse than that, because some of the information on those Chinese web pages are copies in Chinese of information that was available in English. So that information is available to the Chinese speakers and to the English speakers, and you could have gotten it if you'd searched it, been able to search in English. So essentially, the game we want to play is we want to help people who can't find the content that they want to find it. Now, that wouldn't work if we couldn't translate it, and I'm not going to focus on translation here. I'm just going to sort of motivate it with the idea that translation systems are good enough that you might be able to use it. And so the translation system is useless if you can't find the thing that you want to translate. And the search system is useless if you can't translate it. So these are synergistic technologies. And the technology I'm going to focus on today is find me something in another language, right? And we could do this in one of two ways. We could do this by issuing queries in English and searching for information in all the other languages, or any of the other languages, or we could issue the query in some other language and search for information in English. And indeed, the technical challenge of those two problems are essentially the same. And so we do experiments in all kinds of directions, but the killer app is to search English content from non-English queries. By the way, I should say I'm happy to take questions anytime. Apparently, you can't just break in. You've got to type the questions into the chat or into the question area or something. But go ahead and do that, and Marianne will interrupt me and ask your question. And I'd much rather do that than ramble on for an hour. But I can ramble on for an hour if you like. Now, to explain how we do it, I have to tell you a story that goes back to when I was a kid. So I grew up in the 50s and 60s, and I was enamored of elephant jokes. Now, elephant jokes are sort of from this frozen moment in time. Kids of my era thought elephant jokes were just the greatest thing. And some of them are a little politically incorrect today. And the one I'm going to tell is a little politically incorrect now, but you have to hear it to understand why I do this research. So it goes like this. How do you shoot an elephant? You can see why it's politically incorrect, right? It turns out the answer is with an elephant gun, which, as you might imagine, a 6-year-old would just think was the funniest damn thing in the world, but it is actually how you shoot an elephant. That's what elephant guns are designed for. Okay, so next question is, How do you shoot a blue elephant? Now, if you thought about it for a little while, you'd get it. You use a blue elephant gun. You see why it was funny? Okay. Now, the next question that anybody would naturally ask is, how do you shoot a pink elephant? And you might guess you do it with a pink elephant gun. But you don't, because there are no pink elephant guns. All right? You can just see how I was in stitches at this point. So what you do is you hold its nose until it turns blue. Got it? Then you shoot it with a blue elephant gun. Now, little did I know that in my later life, Wikipedia would invent an elephant joke page and would essentially put this joke on as an example. So apparently I wasn't the only person that thought that it was funny. So that's how we're going to do things. This is a picture of a cross-language information retrieval system. This is how it works. So what we do is we issue a query and we want to search some documents. So we take the query and we hold its nose until it turns blue. And then once it's turned blue, once it's in the language of the documents, then we shoot it with a blue elephant gun. And we happen to have one of those, which is a retrieval engine here, a search engine. And that then solves our problem. And so this is what I just showed you. This is the elephant joke in practice. That's what two-lingual is. You issue the query, then you hold its nose until it turns blue. Now it's in the other language, and you then use your blue elephant gun to do the search. Right? Okay. So that's one way to do it. And that searches in the language of the document, which means we can leave the document in its own language. We don't have to run it through translation to every language of the world. We can take queries from any language, translate them into the language of the document, and do the matching in the language of the document. Now, if you thought about this for 3 minutes, you would realize there's another way to do it. And that's you take the documents and you translate them into the query language. Well, this is the same trick, right? You hold its nose until it turns blue. And then now your documents, let's say your queries are in English and you want to search some other language. So now your queries are, and your documents are in the same language. They're both in English. And you can just search in English. So if all your customers are English speakers and they want to do English language search, this is a nice way to do it. You just translate the documents once, and then if somebody actually wants to see one of the documents, you already have a translated copy. You don't have to translate it again. Of course, it's expensive to translate them all in the first place. And if there were lots of query languages, it would be very expensive. Okay, so these are the two obvious ways to do it. But there's a third, and the third one is the one you might not have thought of, right? So here's the third one. What you do is you translate both the queries and the documents into some other language. This seems really stupid, but it turns out it works really well. Right? And so the approach here is you don't translate it into a human language, you translate it into some representation that the machine can use in which the words in one language are represented in a way that's the same, essentially the same, as the words in the other language. Right? So you translate both the query and the document into this abstract meaning representation, and then you do your matching there. Right? And this is the best technique that we have right now. And we do this with a technique called embeddings using deep learning, neural networks. And so I want to give you a taste for how this works. So this is the Rosetta Stone in the British Museum. And you can see here that it has writing in 3 languages. and the writing in 3 languages says the same thing. Now, if you were to have a Rosetta Stone like this, then with some dedicated work, a couple of decades, you could decode a language that you didn't know how to read, like hieroglyphics, using a language you did know how to read, right? You could translate the hieroglyphics into Greek because the words are written in the same order. So you can start to recognize patterns. Now, sometimes the word order reverses, but even those reverses are systematic. So if you have enough, if you have a really big Rosetta Stone and you have a really fast computer, then you could do something like this automatically. And indeed, this is what we do, because today we have really fast computers. And the interesting thing is we have really big Rosetta Stones, because the European Union is just sitting here generating Rosetta Stones every day, right? They're taking the entire proceedings of the European Commission, and they're translating them. The Canadians are making Rosetta Stones every day with their Hansards in the Parliament. The United Nations is making Rosetta Stones every day. In fact, if nobody were making translations, then we wouldn't actually need to translate anything. There'd be no market for it. The market for being able to read things in another language calls forth the translations. And once we have the translations, we can build our automatic Rosetta Stone analyzer, and we are drowning in data. So it doesn't even have to be very good, because once you have a lot of data, very simple systems can learn to translate. And so this is how the machine translation systems are working. And this is what's inside the cross-language search systems. This is how they know how to convert from one language to another. This is the trick of holding its nose until it turns blue. Okay, now the way we actually do it is we get a document, and the document is in some other language other than the query language. So let's say my query language is English, just to be concrete here, and let's say that the document language is in Swahili. Then what I do is I hold up sort of a magic lens, and instead of trying to read the document, what I try to do is I try to count how many times each English word occurs in the document. Well, the English words don't occur in the document, right? I mean, that's just not an English document. It's a Swahili document. But when I look through my magic lens, what I see for every Swahili word is all the English words it could translate to and the probabilities that it could translate to that word, right? And so if I had such a magic lens, I could count how many times I would have expected my English query term to occur in that document. I could do that for every query term. I could do it for every document. And then I could, in exactly the same way that we build monolingual IR systems, build a information retrieval system that searches across languages, because it has this magic lens. So the magic lens is simply the probability of each word in the document language translating to each word in the query language. And so what we want to do is we want to build a machine translation system that doesn't read us what it thinks they said. It reads us what it thinks every word might have been, all the possibilities with probabilities on them. And we can do that in 3 ways. One is on the far left here. We can simply take all the words in the document, and we can have a lookup table that tells us the probability of getting each English word from that document word, right? That's the one on the far left. So that's a technique from the mid 2000s that we developed here at Maryland. The second one is a technique that was developed in a project we participated in. It was actually developed in Massachusetts. The specific version of it that we use by a company called BBN, which was one of the original companies, interestingly enough, that contributed to the design of the internet, So they built the routers that run the internet, but they're working on this problem as well. And they call it a neural network lexical translation model. So this is a neural translation technique. The one on the left was a statistical translation technique. And here, what you do is you look not only at the word in the document, but you look at the words around it. And you try to guess how that word should be translated. So now imagine that that document had been in English, just so that we'll understand the words. And let's say that the word you see in the document is bank, right? And just before or just after that word, you see money. Well, now I know it's not a riverbank we're talking about. And so I know the translations should take account of the fact that it's a financial bank, not a riverbank. And we can learn that using neural networks. And so that's what this neural network lexical translation model, or NNLTM, does, right? The one on the left was called probabilistic structured queries. And so that's a technique from 2 years ago. And the third technique is we simply build a machine translation system, but every time it generates a word, we say, and what if that wasn't the right word? What would your second choice be? What would your third choice be? And here we know not only the sequence of words that are occurring in the document, which we're trying to change into a sequence of words in English, but we also know how likely that sequence of words in English would be, which we don't know in the middle one. So the third one is a technique that we developed here at Maryland 2 years ago, about the same time as the lexical translation model. And now here's the next trick. We know all of these things. We don't just know one of them, and they all make mistakes, but they all make different mistakes. So we can take the one on the left, the one in the middle, the one on the right, and we can ask them to vote on what those probabilities should have been, and we get better probabilities. And you can think that our first lens was a little fuzzy, a little cloudy, but this lens is a little bit sharper now because it's got multiple sources of evidence, right? Okay, so this is what's inside our system. And I wanted to give you a taste for what's inside the system because we're now going to start to think about how people will actually use this, right? And so here's my mental model of how people search. This is
Doug,
yeah.
we have a couple questions that this might be an appropriate time to ask them. And I'm going to give Jason, I'm going to let you ask your question. I'm going to allow you to talk, and then Maureen, I'll let you ask your questions because I think they're relevant to some of the things that Doug was just talking about. So Jason, you should be able to talk.
Can you hear me?
Yes.
I do.
Doug, this is brilliant. I have a one-off question, which is really at the beginning of your talk, which is, has anybody evaluated either Google Translate or something else where you do this iterative process of taking a bunch of text in English and it gets translated into another language, you take that and you translate it back into English, and then you keep doing that back and forth until it's completely ungrammatical, and then you measure the efficacy of the search or of the translation engine by how long it takes to basically make the text ungrammatical?
No, that's not something that I know of having been tried. However, you'll be surprised to know that the people who build machine translation systems actually do that. So what they do is they go out and they get some Rosetta Stone text, some parallel text, is what they call that. So text that's the same in English and the foreign language. And then they'll also get a whole lot of monolingual text. So let's say we're trying to do French, we'll just go get Le Monde. Well, Le Monde hasn't been translated into English, but I mean, we now have an MT system that we built. We just translate it into English and we'll pretend that the machine translation in English is good. And now we'll train on that, right? And so this approach, you can do it in both directions. You can take all the English and translate it into the other language. This is called back translation. And it improves the machine translation system. So that's been done. the problem with the approach you suggest is that the device that's translating in one language in one direction makes mistakes, and the device that's translating in the other direction undoes the mistakes. It makes the mistakes invisible, some of them, because it makes the opposite mistake, right? So if it thinks this is the same as that, it will think that is the same as this. And so it actually gets worse more slowly than you would expect, because it's only the word order that's carrying signal. Its ability to translate the words back and forth. It just, when it goes in this direction, once it reverses it and goes back in that direction, it gets back to the same thing. The only added signal is what it knows about which word orders are licensed in the language. And it gets that by reading a lot of text.
Thanks.
Sure.
Okay, there's another question, and Maureen, you have a couple questions, and I'm going to, you should be able to, oh, hang on. Whoops.
Can you hear me?
I can, yep, okay, you got it.
Okay, so you just talked about how, I'm a former translator, just FYI, and so this is a fascinating topic to me for a couple of reasons. You talked about how it works lexically, the translations. And so how does that work on a larger level, not just on a lexical level, again, across languages that have very different structures? For example, something like Finnish or Russian that has a case system and English does not, or languages that work with an alphabet versus those like Japanese or Chinese, which have a character.
Sure. So let me take the second question first.
Okay.
We don't actually translate words. Back in the early days of translation, that's what we did. We translate word pieces. And so what we do is we drop the entire collection into a statistical system, and we say, find me 1,000 units or 10,000 units or however many we want. We usually use 50,000 units or something, that are units of meaning. Because, in Chinese, there's no spaces between the words in the first place, right? And so what we do is we find sequences. Like, for example, in English, if we do this, we'll see a lot of ing. And so we'll have ing as one of our terms. We call them terms, not words, right? For that reason, so that we don't get stuck on the question of what's a word. And so we'll take unfamiliar words, like, for example, Doug Oard. Doug, you've probably seen before. Oard is an extremely uncommon last name, but O-A-R, is not at all uncommon. And D as a single letter isn't uncommon. We see D sitting by itself all the time. And so we'll just break up my name because we knew nothing better to do with it. Now that breaks it up in a way that is non-compositional. You put it back together, you don't get the same thing. It doesn't mean an or with a D on it. But in a lot of cases, this works. For example, in German, it works really well, because the Germans are just constantly cramming words together and speaking them as if they have no space there. They'll say Fahrvergnügen or something, right? In their Volkswagen commercials. And that's really several words that are being compounded. And so this approach is beautiful for that. And, English has things like this. For example, the word prefix is a prefix, right? And so the pre part of it is actually carrying meaning, and the fix part of it is carrying meaning. And if you split prefix, you still have two useful parts. And so what we do is we build systems that can work across a large set of these. And they learn what that set should be based on the collection that they're working with. That, I think, was responsive to the second half of your question. Tell me the first half again.
Yeah, I was just wondering how these systems work across languages with very different grammatical structures.
Sure.
Whether it's a subject, a verb, a direct object, an indirect object.
Yeah.
So when you're trying to do a translation, not just a single word translation, but trying to translate a full sentence and get make sure it's man bites dog, or is it dog bites man?
Yeah, so it's really cute the way they do these. So a translation system, this is actually a translation system here. This is how a neural machine translation system, which is the state of the art today, works. And you can see here that you come in and you take the words and you convert them into some representation. And so this representation is what I was talking about as the first step earlier, where we could translate it into a third language. This is a third language representation. And then a so-called dense representation. And then these neural components here, which are representing 12 stacked layers. So this is just a sort of a cartoon version, but there are 12 of these stacked on top of each other, are all connected, every unit connected to every other unit. So there are, we have to break the documents up into chunks. The chunks have to be smaller than about 500 words. And every one of those words is connected to every other word. And that's true in the original source language, the language that we're translating from, and in the target language, the language that we're translating to. And we know the relationship between every word and every other word. We know if it's to the left, we know how many words it is to the left. So we know everything about these statistics. Now we have to have an enormous amount of data to train such systems. But once we do, they learn these things. Well, now let's say that you do this in Korean, which is a case marked language, as I understand it. I don't speak Korean. So in Korean, you've got a case marker and a word. And in English, what you want to do is you want to generate an inflected word. Well, so it learns to do that because it knows where the case marker is relative to the word. And it doesn't actually know that it's a case marker or that it's a word. It simply learns how to treat it by just looking at a lot of examples. And so people who first built machine translation systems thought that they were built by following rules. But then later, the statistical approach, and now the neural approach, which is just a non-linear statistical approach, has the idea that language is whatever the heck it is people do. English is creative. You can say anything in English and it's licensed. In French, you could get in a lot of trouble if you said computador rather than ordinateur or something, because the French government would not like that. But real human languages are extensible, and so codifying them in rules is hard, but codifying them in statistics is not hard. I mean, they are what they are. And so if you can see every order of everything, you all of a sudden learn that the relative position of the case marker is meaningless. It's the position of the case, it's the presence of the case marker that matters. And the relative position of a suffix in English is meaningful. And it doesn't appear as a prefix, it only appears as a suffix. And then the system just learns that. It's really very annoying that you really only have to learn one trick and then just show it an enormous amount of data.
Yeah, that kind of addresses my initial question, was that now this is called two-lingual. It looks like it just looks at two languages. You pick two languages. Mm-hmm. What if you're doing something like right now, all the scientists are looking at, COVID and source, where did it come from and how do we treat it and how do we get rid of it and how do we help people who might have it and that sort of thing. So if you wanted to do, say I'm doing a research paper on where are we with COVID right now, would there be a way for me to just say, okay, COVID and, whatever the more scientific term is, SARS, whatever it is, and throw that out there and it's going to search multiple languages at once?
There is, but there's a problem when you do that, which is that the statistics in each of these languages are different. And so I could search all the languages at once and I could show you a tabbed display that would say, okay, your English query is COVID. And here I have documents in Swahili and French and Italian and I don't know.
Okay.
We can do about 100 languages fairly easily now. And so I could show you 100 tabs. But now if you say, show me the most relevant document across all those tabs, they all have scores on every document, and we use those scores to sort the documents best first. But the scores in one aren't comparable to the scores in another. And you can make them comparable, but I will make a lot of mistakes when I do that. And so I can take a guess at it. But that problem of putting, this occurs even when I have two sources I'm searching in the same language. If you tell me to search the New York Times and Twitter at the same time, it's hard for me to properly put Twitter relative to the New York Times. It's not even clear what that would mean. And so it's very hard to do this across languages.
Oh, because of the rule-based system and how different those rule sets are.
Not the rules, because the statistics of the languages are different.
Oh, okay.
Right. I mean, so for example, we might be missing vowels in Arabic, or the vowels
Right.
might be present, right?
Right.
You know, there's vowelized Arabic and non-vowelized Arabic. We might be missing diacritics in Spanish in some sources and have the diacritics in others. It's just a mess.
Okay. Okay,
Right.
great. Thank you.
Yep.
Doug, it sounds like we're heading in the direction of the next part of your talk too. So,
Well, I do want to get on to the next part of the talk, because I think it's where search mastery is the most important,
Yeah.
right? Is how to use this darn thing.
yeah.
Okay. So, so here's here's how I think of an information retrieval system. I think what happens is that the author, when they're trying to say something, picks some words, right? And now I'm oversimplifying, but I think the searcher, when they're trying to find it, picks the same words. You know, if this were controlled vocabulary, then the indexer picks some vocabulary terms and the searcher picks some vocabulary terms, and they meet and everybody's happy. But if it's Google, you just try to guess what words are in the document and put them in your query. As I said, oversimplified view, but take that for a moment as a way of thinking about it. And now imagine that you're trying to pick the words that are in the document, but you don't know the language of the document. Well, you can't do it. So what you do instead is you pick some words in English, and the machine does something, and then it finds some documents for you. And if you try to think about how would a human imagine what the machine is doing, it would look something like this. Well, the machine understands what I said, and then it picks the terms I would have picked if I'd known the language for the thing that I'm looking for, right? So a cross-language searcher has to build a mental model of how this system actually works. And my claim is they'll build a mental model something like the thing on the right, and then they'll try to do it. Now, if you watch people actually use Google, what you'll see is they'll type in, you know, happy, happiness, happier, because they want to see, is it paying attention to the way that I write my word? And then they'll write very happy to see, is it paying attention to two words? They'll write happy very. I mean, people poke around and they try to understand what's going on, right? Not everybody takes a course in search mastery, but there's a lot of poking around going on. And so the systems have to support poking around. And it's not clear to me what poking around in an elephant joke would look like. So if they've even heard the elephant joke. Okay, anyway, so this is the problem we have to solve. We have to somehow make these systems understandable. Now, I want to talk about two ways that we've tried to do this. Neither one of which is a complete solution, but they both sort of point in the direction of something that, you know, search mastery really ought to take on and solve for us. So this is a project that we're just finishing. In fact, we just finished it. Well, we had our last meeting today, and the final report is due tomorrow. We've been working on it for 4 years. And the way that this project is set up is that the phone rings 9 times in 4 years. And each time the phone rings, they give us a language. And so they, you know, they called up and they said Pashto one day. And we're like, okay, Pashto. And then we have to go off and build a system that searches Pashto. Now, the trick is it doesn't search just Pashto newspapers. It searches all kinds of Pashto text, like Pashto blogs and stuff like that. Okay. But it doesn't just search text. It searches Pashto speech, right? And I mean, they called up and they said Bulgarian one day, and they said Lithuanian, and they said Somali, and they said Swahili, and they said Persian. I mean, they just, you know, just all over the place, Tagalog. And so every time the phone rings, we have to do this. And what we do is we go build a system that can process speech in whatever language they told us, and translate that speech into English, find the things that they're looking for. They give us a list of queries. They give us a list of what we should find for those queries to measure how well we're doing. And then summarize the results in English, right? So that's the task. And here's the system. And so what we've done here is we've typed in the query Ebola. We're going to search text. And this is the first document we get. And your task is figure out, is this really about Ebola? And then you can see the second document there. And if you scroll down, you see more. And of course, you might want to see the documents. But the documents are in Pashto. So there's the document. If you read Pashto, you can do that. Or here's the document in English. This is just Tulingual again, right? I mean, somebody sent us $10 million to rebuild Tulingual in Pashto. Except we can do it in speech too. So here it is processing Pashto speech. So in comes the query Ebola. There we go. There's a speech recognition, then machine translation, then summarization. There's the document, right? Darn thing works in speech. And we can measure how well we do. And so it's sort of a black art to evaluate these things, but we have queries that tell us what we're supposed to search for, and we have an answer key that tells us for each document in a relatively small set of documents. So this is, I don't know, 10,000 documents, whether that document is relevant or not to that query. So somebody paid a fortune to develop this answer key for us so that we could figure out whether it was any good, the systems we were building. And we built them for 9 languages, but they didn't give us the answer key for one of them. They kept it secret so that they could tell if we were really doing well, or if we were just sort of, training to the test. And so this is the results for the 8 languages where we have the answer key. And what you can see here is 4 systems that we built. This was a joint project between Columbia University, Yale University, University of Edinburgh in the UK, Cambridge University in the UK, and the University of Maryland. And the people in Edinburgh built a neural machine translation system. And we simply said, oh, thank you very much. We'll just hold its nose until it turns blue. It'll be English and we'll search it. And you can see how well that works. If you try to do it in Swahili, you get 0.25. Now, I got to tell you what 0.25 means. That's 25% of perfect. So if we put all the documents that are relevant first and then all the other documents, we get 1. And we got 0.25, right? But this system I showed you, probabilistic structured queries, the very simple system, for this case where we're Pashto, we don't have a lot of data, we can get 0.36. Well, 0.36 is way better than 0.25, and you should buy the 0.36, right? We have a couple of other things. People here at Maryland made a neural machine translation system. It was, not quite as good as the one at Edinburgh. We made a statistical machine translation system that was about as good as the neural system. This is an earlier technology. And then we put the 4 systems together, add them up, divide by 4 sort of an approach. And we don't do quite as well as the best single system. Then the next language they gave us was Somali. Now the 4 system combination is better than any of the others. You can see Somali is a much harder language. And the reason for this is that in Swahili, there's a fair amount of business. Somali is not a large commercial economy. It's not spoken in, is spoken in Somalia, which has got serious problems with governance. And so it's not well standardized. And so what Somali is varies depending on who's writing it and who's speaking it, much more so than for Swahili. And of course, for Bulgarian and Lithuanian, they're much easier languages. You can see how well we do here. So you can see that the scores are systematically lower on the harder languages and higher on the easier languages. Down to here, that's the 4-system combination. But the thing I want to focus on is, what if I said something like what you say when you play pool? I'll call my shot 8-ball in the corner pocket. So, you know, when you do a search in Google, you just go down as far as you like in the list. Nobody ever goes to the second page, but you go to the third one or the fifth one, or you could go to the 25th one if you wanted to. But if you're paying somebody to do translations of these, as you might if you were, doing diplomacy with this or something like that, then you'd really want the machine to draw a line and cut it off and say, don't go any further than this, right? And so the nice thing about this score, which is called the actual query weighted value, is that this is the maximum value we could achieve, and this is the value we actually achieve when we say, okay, cut it off there. So for each query we look and we guess how far down the list you should go. And you can see that by the time we get to the end in Georgian, the last language that we did, we're doing pretty darn well. We're getting very close to the best that can be done. In fact, we're doing better than the best that can be done because of the way in which we're measuring the best here. So this isn't actually the best, but it's pretty close. But then this is just 4 systems combined. The beauty of cross-language IR is we have all these ways of building information retrieval systems and all these ways of translating, and we put them together and take advantage of that diversity. And so you can see here how the diversity works for us. We actually submit many more than 4 systems, many variations, typically 10, 12 systems, put them together, and you can see we're getting 82% of perfect, 80% of perfect, 82.3% of perfect. And these are calling our shot, saying, cut it off there. This is actually fairly amazing, I think. So the point here is we can tell you where to stop paying for translations, right? That's one thing that is sort of peculiar to the cross-language search that you might do. Now, if you want to see how we do in speech, you can see here, except for this one mistake we made, we're doing not quite as well in speech in general, but the same basic techniques are working. We're working reasonably well. We're not at 80%, we're at 70% of perfect. But the speech systems are pretty good in languages that, I don't know, I didn't know there was a Kazakh. Georgian is spoken, by the way, in the country Georgia, not in the state Georgia. Okay. Next thing is, what if we just, instead of that, just ask you a question, right? Now, the question I always want to ask, you can guess who's paying for all this stuff, right? Is the Intelligence Advanced Research Project activity. And you can see why they'd want to know what's going on in Kazakh, right? But the question I want them to ask is questions like, should I invade Iraq? A question where the answer is yes or no. And you'd hope they get no, but anyway. So if you look at people's ability to answer questions, this is work we did a long time ago, it was in 2004. But here what we did was we did a cross-language search, and then we showed people translations, and we just asked them questions, and we saw how many questions they could answer. And we had to be careful, because these were Americans, not to ask them questions that they already knew the answer to. So for example, you couldn't ask them, what was the date of Pearl Harbor, because too many Americans know the answer to that. But we could ask them, who's the managing director of the International Monetary Fund? And trust me, there's almost no American that knows the answer to that one. How many human genes are there? My very favorite question was, when did Lenin die? Because to answer that question, as you're reading stuff, you have to first realize this is not John Lennon, right? And Americans aren't so good at that one. And once you've got that, then you have to find a document that says it. And there's only one document in the collection, and it doesn't even say it. What it says is, last Thursday, the 50th anniversary of Lenin's death. And you've got to find that in Spanish, understand it, and calculate it. And it turns out that people did this, right? there were 3 people who found it, but only 2 of them who could do math, right? And what they did was they literally wrote the answer down on a napkin or on a piece of paper. And then we just had assessors look and see if that was the right answer. And look at this. We asked them 16 questions, and 3 of the questions were so easy, everybody got them. Who's the managing director of the International Monetary Fund? You had to read Spanish documents to find this in 2004. This is an easy problem, right? And the reason this is an easy problem is managing and director and international and monetary and fund are all easy words to translate, right? Lenin is a harder word to translate. We don't see it very often. How many human genes are there? There are only 2 useful words in there for searching. And you find a whole lot of other stuff about humans or about genes. And so this is a harder problem than that one. This is a harder problem than that one. And you can see why. Okay, but this now we have a probe. We have the ability to measure. Right? Alrighty, let me wrap up with just a quick word on what we aren't yet able to do. So I've been telling you that the people who are going to search the same way everybody else searches. They're going to type in a query and they're going to get an answer. Okay, so here's a list of all the internet user, or a picture of all the internet users in the world. And the thing I want you to focus on here is sub-Saharan Africa. All right, so sub-Saharan Africa has got, like nobody on the internet. Now it's got a few people on the internet, but this is a very small fraction of 1 billion people in sub-Saharan Africa. And so you're not going to grow the Europeans on the internet or the North Americans on the internet or even the Chinese on the internet very much in the future, but you can grow the people in sub-Saharan Africa on the internet. Problem is, there are a lot of people in sub-Saharan Africa who don't know how to read and write. And now cross-language search doesn't do them any good. You actually have to find content that is spoken and speak it, right? Not convert it to text and then translate it. You actually have to have spoken content. And you have to have spoken content in languages where people might not pay you to do that. And so you're going to have relatively weak search systems. And we built search systems we built a search system for Gujarati, a language spoken by about as many people as speak Dutch, but about half of them are low literacy in Gujarat in India. And we can do matching, sounds like matching, right? You speak, we find people who spoke with similar sounds and we match them just like we do for everything else. It's relatively weak, but if we had a long query and a long document, we'd have a good chance of getting you a match. The question is, how do we get a long query? And so I want to leave you with something to think about here. And that is that we always design things by analogy to what existed before. And when we're searching, when we type in the query and we see 10 blue links, that's because that's what we did before when we were searching in text in a single language, but it's not necessarily the right thing to do for speech. And we've seen this problem before, right? I mean, so here's a picture of an early car. It was designed to look like a carriage because that's what people thought you got in when you wanted to go someplace. This is an early light over here, and you can see that it's got a wick. I mean, because that's what lights had, right? They were candles and they had wicks. And so early lights were made to look like candles. And then they had to put up a sign to tell you, don't attempt to light the light with a match. Use the key on the wall by the door. And it's like, the key? It's like, yes, because I couldn't tell you to use the switch. They don't know what a switch is, but they know what a key is, right? You can turn a key. And so they literally used keys to turn on the lights that had the wick that you weren't supposed to light. You can see we're doing the same thing with the 10 blue links. And so we tried doing an experiment where we took the thing on the left and we said to people, imagine you don't know how to read and write, right? And imagine that you're going to do a search and you've never seen a search engine before. So you don't know about this 10 blue links thing before. And just babble. Just talk about what you're looking for. So read this thing. This is somebody who can read and write. This was at IBM Research India. And then keep this in your mind and babble for us. And so they did. And so this is what they said. So a long time back, a friend of mine had a Toyota Prius, uses electric and petrol to reduce the consumption. I mean, you can just see it's very messy. And we're like, man, this is great. I got lots of words. And we took their words and we matched them to words in a document. And we asked the system, when did we find an answer in position 1? Right? Because there's no 10 blue links in speech, right? I mean, we're either going to barge in with an answer or we're not. And so we knew on the third babbler that they had gotten there after about 30 words. We could barge in and give an answer, right? Babbler number 2 never makes it. Babbler number 1 makes it at about 50 words. So if people will give us long enough queries, if people just stop typing short queries, the search engines can work to search speech to speech, right? And then we tried to guess, can we learn when to stop? And so here we are learning to stop with Babbler 1. So with Babbler 1, we should stop here at about 50. And our system doesn't stop until about 62. Well, that's not bad, right? So it's just a quick experiment to give you an idea that everything I've shown you so far is wrong, because we've been making electric lights with wicks turned on by keys. And what we need is fluorescent lights or LED lights that are turned on by talking to Alexa. Oh, that's not going to work. Alexa's going to turn on now. Okay. Anyway, what do I want you to know? Well, we can reach new users. We can reach users who don't know English. We can reach users who don't know how to read and write. We can cross language barriers. We can work with speech. We can put all these things together, but we need you to think about how it's going to be used. And so if you want to see what we've been doing, you can read these things. And I'd be happy to talk to anybody who's interested in seriously thinking about what it is we ought to be doing. And that's it.
Thank you, Doug. We have a couple questions. We're running a little bit close, but I think we have time for the most recent one. Let's see. I understand the case for deliverables for applications whose market value may be too low to merit industry effort. But what is the state of the art for academics contributing new ideas for markets in which industry dominates?
That's a great question. So there are some things we can't do. So for example, if I really want to know how to build a search engine, what I want to know is which documents are relevant to which queries. And I'd like to have that for a bazillion queries or maybe 2 bazillion queries. And Google has that because every time you do a search, you either click on something or you don't, and they can take that as a signal. So all I want is I want all the searches that were ever done in Google and all the clicks. And of course, you won't give that to me. I mean, America Online gave out a query log at one point, and they were on the front page of the New York Times a week later with a picture of one of their users. Because once I see all your queries, I mean, everybody searches for themselves. It's pretty easy to figure out who's doing the search. And so you have to do that kind of work in a company. And now it's a little scary that the companies are doing it, but you sure as heck don't want to give that information away to the public. And you probably don't want to give it to academics. And so we send our students to these companies to work with that kind of data, but we don't have that data ourselves. On the other hand, the companies aren't going to solve this problem. There's no money to be made in this cross-language search space because the companies make money by showing advertisements, and the advertisements are to users in places that have lots of money. And the people that are in places that have lots of money speak one of like 10 languages. And so this is a problem where academics are exactly the people you want working on the problem. And the technology to do the translation doesn't require any special access to data. I mean, you know, as I say, the European Union is generating it, the UN's generating it. There's lots of translation data around. So academics can build the technology, but we can't build the systems people use because we lose interest in 3 years and want to go work on some other project, and we need a company to do this. And so the real problem is getting ideas, not getting resources into academia, it's getting ideas out of academia and into companies that can actually go build these things, or into government agencies or whatever. And it's not hard to get it into some government agencies because they've got a lot of money and really important problems. But getting things commercialized requires that then you have academics who are not good at commercializing, trying to figure out how to make a business out of this. And you know, the one thing we know is the best predictor of success in starting a business is having failed at attempting that before. And academics haven't even failed yet. And so the problem isn't so much getting us the data. We can get pieces of it that we need, but then getting it back out and commercialized is the biggest challenge.
Okay, thank you, Doug. There are a couple more questions. Unfortunately, we're out of time. So I know Doug's been very generous in offering his availability for people who have questions. So if you'd like them answered, you can reach out to Doug. And just to wrap up here, I want to thank everybody for coming to the speaker series. And first of all, I want to thank Doug for really for a wonderful talk. And there are some really great comments in the chat telling expressing how interesting this was. So I hope you will. So thank you all for coming, and you're welcome to join us for the next session on November 18th. We'll have Michael Schechter, who's the Vice President for Growth and Distribution at Microsoft. He's had a significant history in developing the Bing search engine, and he's also a University of Maryland alum from the computer science department. So he'll be here at the same time, 11 to 12 on November 18th, and so look for those announcements about that talk in November. So thanks again, Doug. I really appreciate it. And thank you, everybody, for joining us. We'll see you all next time.